At the dawn of the 20th century, the world of physics was on the brink of a revolution, though few realized it at the time. Scientists had built a towering structure of knowledge based on classical physics, a framework that seemed unshakable. Newtonian mechanics had explained the motion of planets, the trajectories of projectiles, and the behavior of objects in everyday life with astonishing precision. James Clerk Maxwell's equations had unified electricity and magnetism, showing that light itself was an electromagnetic wave. For decades, physicists had believed that the laws they had discovered were universal, governing everything from the largest stars to the smallest particles. Yet, as they examined certain phenomena at the atomic and subatomic level, cracks began to appear in this elegant structure. One of the most confounding puzzles was the phenomenon of Blackbody radiation, the radiation emitted by heated objects. Classical physics predicted that as objects got hotter, they should radiate energy at increasingly higher frequencies, ultimately leading to an infinite release of energy. This glaring contradiction between theory and observation came to be known as the ultraviolet catastrophe. It was a problem that classical laws simply could not resolve, and it left the scientific community puzzled and frustrated. In the midst of this uncertainty, Max Planck, a German physicist, emerged as a quiet but determined figure willing to challenge the conventional thinking of his time. Planck was deeply concerned with understanding the relationship between heat, energy, and radiation. He sought a solution not merely through speculation, but through careful mathematical reasoning and empirical evidence. His approach was meticulous and methodical, grounded in a belief that nature must have an underlying order, even if it eluded the grasp of existing theories. After years of study, Planck proposed an idea that was both radical and profound. Energy, instead of being emitted or absorbed continuously, is delivered in discrete packets, which he called quanta. This notion fundamentally contradicted the classical assumption that energy flows in a smooth, uninterrupted manner. By introducing the concept of quantization, Planck was able to reconcile theoretical predictions with experimental observations, providing an accurate explanation for Blackbody radiation that classical theories had failed to achieve. The introduction of energy quanta was not just a small adjustment to existing equations. It was a revolutionary shift in how physicists understood the natural world. Planck's work implied that, at a fundamental level, energy comes in finite amounts, measurable and distinct, rather than in an infinitely divisible continuum. This idea was initially met with skepticism. The concept seemed almost heretical, challenging centuries of accepted knowledge about the continuous nature of energy. Yet, the elegance and predictive power of Planck's formulas could not be denied. His constant, later known as Planck's constant, became a cornerstone in physics, representing the scale at which quantization effects become significant. The discovery provided not only a solution to the ultraviolet catastrophe, but also laid the groundwork for an entirely new branch of science, quantum physics. The significance of this development extends far beyond the problem of Blackbody radiation. Planck's insight forced scientists to reconsider the very foundations of physics, opening the door to questions about the behavior of atoms, electrons, and photons that classical mechanics could never adequately explain. It challenged the notion that the universe was entirely predictable in a deterministic sense, suggesting instead that uncertainty and probabilistic behavior might be intrinsic features of the natural world. In doing so, Planck planted the seeds for a century of scientific innovation and discovery, influencing figures such as Albert Einstein, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, who would each contribute to the development and expansion of quantum theory. In retrospect, the story of this period in physics is a powerful reminder that progress often comes not from confirming what is already known, but from confronting anomalies and daring to question the assumptions that underpin our understanding. The struggle to explain Blackbody radiation was not a minor footnote in the history of science. It was a catalyst that reshaped the trajectory of modern physics. Planck's insight showed that even in the face of overwhelming skepticism and deeply entrenched beliefs, bold and careful thinking could uncover truths that forever changed the way humanity perceived the universe. By revealing the discrete nature of energy, Max Planck not only solved a pressing scientific puzzle, but also ignited a revolution that would transform technology, philosophy, and our comprehension of reality itself. Max Planck's proposal that energy is emitted in discrete units, or quanta, was not just a mathematical trick. It represented a profound shift in the way scientists viewed the natural world. Before this breakthrough, the prevailing belief was that energy could vary continuously, like the smooth flow of water in a river. Classical physics had long assumed that energy could be divided infinitely, with no smallest unit, and that any change in energy levels occurred in an uninterrupted, gradual manner. However, experimental evidence stubbornly refused to align with this assumption. The problem of Blackbody radiation, for example, exposed the limitations of classical ideas. When objects were heated to high temperatures, they emitted radiation in ways that the existing laws could not explain. According to classical predictions, the intensity of radiation should increase without limit as the frequency rose, leading to the so-called ultraviolet catastrophe. In reality, experiments showed a clear limit. Energy emission at high frequencies did not spiral into infinity, but instead followed a precise pattern that classical physics failed to predict. This discrepancy demanded a completely new way of thinking about energy and matter, and Planck's quantum hypothesis provided exactly that. By suggesting that energy is quantized, Planck introduced the revolutionary idea that energy exists in discrete packets, each proportional to the frequency of the radiation it carries. These packets, which would later be called photons, implied that energy could not take on just any value, but could only change in specific steps. This concept was initially difficult for the scientific community to accept because it defied intuition and challenged centuries of continuous reasoning in physics. Yet the genius of Planck's idea lay in its ability to reconcile theory with experiment. Through rigorous calculations, he demonstrated that by assuming energy quantization, the behavior of Blackbody radiation could be accurately predicted across all frequencies. What once seemed like an insurmountable problem became elegantly solvable. This achievement not only cemented Planck's reputation as a brilliant physicist, but also marked the birth of quantum theory, which would eventually redefine the entire field of physics. The implications of Planck's discovery were far-reaching. By establishing that energy changes occur in discrete steps, he challenged the deterministic world-view that had dominated science for centuries. In classical mechanics, every motion and interaction could, in principle, be predicted exactly if the initial conditions were known. With quantum theory, certainty gave way to probabilities. Energy transitions at the atomic and subatomic level were no longer continuous and predictable in the traditional sense. They occurred in quantized leaps, introducing a fundamental unpredictability into the behavior of matter and radiation. This shift forced scientists to rethink basic assumptions about reality itself. It suggested that at its most fundamental level, nature operates according to rules that are far stranger and more nuanced than the smooth, continuous processes described by classical laws. Furthermore, Planck's work laid the essential foundation for subsequent breakthroughs in atomic and subatomic physics. Without the concept of quantized energy, many of the discoveries of the early 20th century, such as Niels Bohr's model of the atom, Albert Einstein's explanation of the photoelectric effect, and development of quantum mechanics would have been impossible. Planck's constant, a numerical value that sets the scale for quantum effects, became a fundamental constant of nature, appearing in equations that describe the behavior of particles, waves, and photons. It is a bridge between the macroscopic world we experience daily and the microscopic universe of atoms and subatomic particles. The recognition that energy is not infinitely divisible opened a door to a new understanding of matter, radiation, and the forces that govern their interactions. Planck's insight also had profound technological and philosophical consequences. The concept of quantization paved the way for innovations such as semiconductors, lasers, and modern electronics, all of which rely on precise energy transitions at the atomic level. Philosophically, it reshaped our perception of reality, showing that the universe is not entirely deterministic and predictable, but is instead governed by fundamental rules that combine certainty with chance. It reminded scientists and thinkers alike that nature often defies intuition, requiring new frameworks and bold ideas to understand its deepest workings. Max Planck's contribution is a testament to the power of imagination guided by rigorous analysis. By daring to propose that energy is quantized, he not only solved a pressing problem in physics, but also opened a pathway that would lead to some of the most revolutionary discoveries in human history. His idea was a seed that grew into the towering edifice of quantum physics, forever changing the way we see the universe. The introduction of energy quanta marked not only a solution to the immediate problem of Blackbody radiation, but also laid the foundation for an entirely new perspective on the natural world. Before this revolutionary idea, the prevailing view in physics was that energy, matter, and the forces acting upon them could be understood as continuous and predictable. Classical physics had provided an incredibly successful framework for describing the motions of planets, the behavior of fluids, and the properties of light as waves. It was a universe of smooth trajectories, continuous variations, and exact predictions. Yet, when scientists began probing the behavior of matter and radiation at very small scales, these assumptions began to fail. Phenomena at the atomic level revealed inconsistencies that classical laws could not account for. The precise measurements of spectral lines emitted by heated gases, the behavior of electrons in atoms, and the very nature of light itself were all at odds with the notion of continuous energy. In this context, Planck's insight that energy is quantized was nothing short of revolutionary. By proposing that energy is emitted or absorbed in discrete packets, Planck introduced a fundamental shift in understanding. These packets, each proportional to the frequency of the radiation, suggested that nature operates in steps rather than smooth flows. In effect, Planck was revealing that the microscopic world obeys rules that differ radically from those of the macroscopic universe we observe with our senses. The idea that energy exists in finite, indivisible units allowed scientists to accurately predict the intensity of Blackbody radiation across all frequencies. This simple yet profound adjustment resolved the ultraviolet catastrophe and demonstrated the extraordinary explanatory power of the quantum concept. It was the first time that experimental observations and theoretical predictions aligned in a situation that classical physics had failed to describe. The success of Planck's hypothesis was not just mathematical, it was a glimpse into the hidden structure of reality, suggesting that the universe at its smallest scales is governed by entirely different rules. Planck's discovery quickly became a cornerstone for the next wave of theoretical advancements. While he himself approached the idea cautiously, seeing it largely as a mathematical convenience, the implications were enormous. It opened the door for other physicists to explore the strange and counterintuitive properties of the atomic and subatomic world. Albert Einstein, for instance, would later apply Planck's quantum concept to explain the photoelectric effect, showing that light itself is composed of particles called photons. Niels Bohr would build on this foundation to propose his model of the atom, where electrons occupy specific energy levels rather than moving in continuous orbits. Planck's insight thus became the key that unlocked the door to modern quantum theory, influencing generations of scientists who would go on to develop the rich, complex framework we now call quantum mechanics. Beyond its theoretical significance, the quantization of energy has profound practical and technological consequences. The recognition that energy changes occur in discrete steps is the principle behind countless innovations in the modern world. Lasers, semiconductors, and quantum computers all rely on the predictable transitions of energy between quantized states. Even the technologies we use every day, from smartphones to medical imaging devices, owe their existence to this understanding of energy at the quantum level. What began as an abstract solution to a theoretical problem became the bedrock for an era of scientific and technological advancement that has transformed society in ways Planck could scarcely have imagined. Philosophically, the introduction of quanta forced a reconsideration of how we understand reality. Classical physics had suggested a universe that is deterministic, predictable, and continuous. The quantum hypothesis introduced an element of discreteness, a world where certain processes occur in distinct steps and probabilities govern outcomes at the smallest scales. It challenged the notion that nature could be fully described by smooth, predictable laws, revealing a universe that is simultaneously ordered and strange, comprehensible and mysterious. This shift has influenced not only physics but also philosophy, shaping debates about the nature of reality, error in message stream rate. The introduction of Planck's constant into physics was more than just a mathematical convenience. It became a cornerstone that reshaped the very foundations of science. Before Planck, physicists believed that energy could vary smoothly and continuously without limits. The classical view held that energy levels could be infinitely divided, that heat, light, and motion were all part of a seamless flow. Planck's revolutionary insight challenged this notion by suggesting that energy is quantized, that it exists in discrete, indivisible packets, each precisely proportional to the frequency of radiation it carries. The proportionality constant that links energy to frequency is what we now know as Planck's constant. Its introduction represented a profound paradigm shift, a single number that encapsulated a fundamental property of the universe. Though it may seem like an abstract concept, this constant has real, tangible implications, influencing everything from the behavior of electrons in atoms to the very nature of light itself. The significance of Planck's constant is best understood by examining the problems it helped solve. Classical physics struggled to explain the spectrum of light emitted by heated objects. According to the existing theories, as the temperature of a blackbody increased, it should radiate energy with ever-growing intensity at higher frequencies, eventually diverging toward infinity. This prediction, famously known as the ultraviolet catastrophe, was not just a minor error. It represented a fundamental failure of classical theory. Experiments, however, told a very different story. The radiation curve peaked at certain frequencies and then declined, defying the expectations set by classical models. Planck approached this problem not by adjusting existing formulas, but by rethinking the nature of energy itself. He proposed that energy could only change in fixed, discrete amounts quanta, and that the size of each quantum was determined by his constant. This simple yet radical idea provided an exact match to experimental data, explaining the previously inexplicable patterns of blackbody radiation with remarkable precision. The impact of Planck's constant extended far beyond the solution of a single problem. It fundamentally altered the way physicists understood the microscopic world. By introducing a natural scale for quantization, Planck effectively defined the boundary between classical physics and the quantum realm. At energies and scales where Planck's constant is negligible, classical laws still work perfectly, which is why Newtonian mechanics continues to describe the motion of everyday objects. But at atomic and subatomic scales, where the influence of Planck's constant becomes significant, quantization dominates. This insight provided a framework for exploring phenomena that were previously mysterious, such as the discrete energy levels of electrons in atoms, the photoelectric effect, and the behavior of photons. It established a bridge between observable macroscopic phenomena and the hidden, quantized nature of the microscopic world. Moreover, Planck's constant became a unifying principle in physics. It links the energy of a photon directly to the frequency of electromagnetic radiation, forming the foundation for the entire field of quantum mechanics. Its introduction marked the moment when physics transitioned from a deterministic, continuous description of nature to one that embraces discrete steps, probabilities, and fundamental uncertainty. This shift was not just mathematical, it was philosophical. The universe, as Planck revealed, operates according to principles that defy classical intuition. Energy is not infinitely divisible. Time and motion are not always smooth, and the microscopic world behaves in ways that challenge everyday perceptions of reality. Planck's constant quantifies this strangeness, giving scientists a precise tool to measure and predict phenomena that were once considered mysterious or paradoxical. The practical consequences of Planck's constant are enormous. Every modern quantum technology, from semiconductors and transistors to lasers and quantum computers, relies on the principles it embodies. Understanding energy quantization allows engineers to manipulate electrons in circuits, design precise lasers, and develop devices that exploit the unique properties of the quantum world. Beyond technology, Planck's constant has also profoundly influenced scientific thought, inspiring generations of physicists to explore the limits of knowledge and the structure of reality itself. It serves as a reminder that a single, seemingly abstract insight can have ramifications across science, technology, and philosophy. Ultimately, Planck's constant represents more than a number, it embodies a revolution in thought. By introducing a fundamental scale to energy, Max Planck opened the door to a universe of discrete, quantized phenomena that would reshape physics for generations. It allowed scientists to reconcile theory with experiment, challenged classical assumptions, and laid the groundwork for the extraordinary developments of the 20th century. Planck's constant is not just a measure of energy, it is a symbol of human curiosity, of the willingness to question the obvious, and of the courage to propose bold ideas that forever change our understanding of the cosmos. Niels Bohr entered the world of physics at a time when the atom remained a profound mystery. Scientists knew that atoms were composed of a dense nucleus surrounded by electrons, but the behavior of these tiny particles defied classical explanation. According to the laws of classical mechanics, electrons orbiting the nucleus should constantly emit energy as radiation, gradually losing speed and spiraling into the nucleus. This would make atoms inherently unstable, a prediction that obviously contradicted the reality of stable matter. The prevailing theories could not explain why atoms did not collapse or why they emitted light in specific patterns. It was a puzzle that demanded a radical rethinking of the atomic structure, and Niels Bohr was the visionary who would provide it. Bohr's brilliance lay in his ability to combine empirical evidence with daring theoretical insight. He proposed that electrons do not radiate energy continuously as they orbit the nucleus. Instead, they occupy fixed energy levels or shells, each with a specific quantized energy. These energy levels act as safe zones, where electrons can exist without losing energy, defying the predictions of classical physics. When an electron jumps from one energy level to another, it either absorbs or emits a discrete amount of energy in the form of light. This idea directly explained the emission spectra of hydrogen, which had long puzzled physicists. The spectral lines were no longer mysterious. They were the visible signature of electrons transitioning between fixed energy states. Bohr's model elegantly bridged the gap between the quantized world of energy introduced by Max Planck and the observable phenomena of the atom. It demonstrated that quantization was not merely an abstract mathematical tool, but a fundamental feature of nature. By placing electrons in discrete energy levels, Bohr solved the paradox of atomic stability. Atoms could now be understood as structured, predictable systems, each with its own set of quantized electron orbits. This insight was revolutionary because it challenged centuries of assumptions rooted in classical mechanics, showing that the microscopic world operates under rules that often defy our macroscopic intuition. The impact of Bohr's theory extended far beyond explaining hydrogen spectra. His model laid the foundation for understanding chemical behavior and bonding. The arrangement of electrons in quantized orbits determines how atoms interact, combine, and form molecules. Bohr's work provided a scientific basis for the periodic table, linking electron configurations to elemental properties. It illuminated the reasons behind chemical stability and reactivity, offering a clear explanation for patterns that had previously been observed but not fully understood. His ideas transformed chemistry and physics, revealing the deep connections between atomic structure and the behavior of matter. Bohr's contributions were not limited to theoretical insights. They also inspired a new generation of physicists to explore the quantum world. His model encouraged scientists like Werner Heisenberg, Erwin Schrödinger, and Paul Dirac to develop the more comprehensive frameworks of quantum mechanics, which would eventually describe atoms and subatomic particles with unprecedented accuracy. Bohr's concept of quantized energy levels, combined with his principle of complementarity, also influenced philosophical discussions about the nature of reality. It suggested that the universe is not entirely deterministic, and that observation plays a fundamental role in shaping what can be known about a system. This profound shift in thinking challenged the deterministic world view that had dominated science since Newton and opened the door to a universe governed by probabilities, uncertainty, and wave-particle duality. Moreover, Bohr's ideas had technological implications that continue to resonate today. The understanding of electron transitions in atoms is central to the development of lasers, semiconductors, and many modern electronic devices. Bohr's vision allowed scientists and engineers to manipulate atomic and subatomic systems in ways that have transformed technology, medicine, and communication. His model, though simple compared to the full complexity of quantum mechanics, remains a cornerstone of physics education, introducing students to the principles that underpin modern science and technology. Niels Bohr's genius lay not only in solving the puzzles of his time, but in laying a conceptual foundation for the future. By introducing fixed energy levels for electrons, he provided clarity to the chaos of atomic behavior, connecting quantization with observable phenomena. His work bridged the gap between theory and experiment, showing that bold, imaginative thinking, grounded in evidence, could uncover profound truths about the universe. Bohr's model did more than explain the atom. It opened a window into the quantum realm, forever altering the way humanity understands the building blocks of reality. Bohr's model of the atom represented a radical departure from the classical ideas that had dominated physics for centuries. One of the most striking and influential aspects of his theory was the introduction of fixed energy levels for electrons, a concept that directly addressed the long-standing mystery of atomic stability. In classical physics, electrons orbiting the nucleus should continuously radiate energy, much like a charged particle moving in a circular path. This radiation would cause the electron to lose energy, spiral inward, and eventually collapse into the nucleus, leading to the destruction of the atom itself. Yet matter in the universe is remarkably stable. Atoms maintain their structure over billions of years, and the very fabric of life depends on this stability. This apparent contradiction was a major crisis in physics, one that classical mechanics could not resolve. Bohr's insight provided a solution that was both elegant and transformative. According to Bohr, electrons do not occupy arbitrary positions around the nucleus. Instead, they exist in discrete energy levels or shells. These levels are quantized, meaning that electrons can only reside in specific orbits, each with a fixed energy. While in these orbits, electrons do not radiate energy, which explains why atoms are stable despite the classical prediction of inevitable collapse. This idea, simple in principle but revolutionary in concept, solved the problem that had perplexed physicists for decades. It suggested that the microscopic world does not adhere to the smooth, continuous behavior that classical physics assumed, but instead follows distinct, quantized rules that govern the behavior of particles and energy at the atomic scale. The quantized orbits also provided a clear explanation for the emission and absorption of light. When an electron moves from one energy level to another, it absorbs or emits a specific amount of energy, corresponding exactly to the difference between the two levels. This energy is released in the form of light or electromagnetic radiation, producing discrete spectral lines that had long been observed but remained unexplained. By linking these spectral lines to electron transitions, Bohr not only accounted for the structure of the hydrogen atom, but also provided a framework for understanding the behavior of other elements. The spectral lines, once mysterious streaks in a laboratory experiment, now became a direct reflection of the underlying quantum structure of the atom. Bohr's theory bridged the gap between abstract quantum concepts and observable reality. It demonstrated that quantization is not just a mathematical abstraction, as Max Planck had originally proposed, but a fundamental characteristic of nature that governs the stability and behavior of matter. The idea that electrons occupy fixed energy levels introduced a new layer of order to the atom, transforming it from a chaotic collection of charged particles into a structured, predictable system. This understanding laid the groundwork for the development of more sophisticated quantum mechanics, which would later explain complex atomic interactions and chemical behavior with even greater precision. Moreover, the concept of fixed energy levels revealed a profound insight about the universe. Stability and structure at the microscopic level arise from quantized rules that differ radically from the familiar laws of the macroscopic world. Electrons are not free to exist anywhere or to radiate energy continuously. They are bound by the rules of quantization, and these rules dictate the unique characteristics of each atom. This realization had far-reaching implications, influencing not only physics but also chemistry, as the arrangement of electrons in these quantized orbits determines how atoms bond, interact, and form the diverse range of substances found in nature. Bohr's model also inspired a philosophical shift in how scientists approached the microscopic world. It suggested that observation and theory must be integrated in a new way, recognizing that the behaviors of electrons, photons, and atoms follow probabilistic and quantized patterns rather than continuous, deterministic ones. The notion of discrete energy levels introduced an element of predictability in a domain that previously seemed chaotic, yet it also highlighted the strangeness of the quantum world, where particles behave in ways that defy everyday intuition. The practical implications of Bohr's concept of fixed energy levels have been profound and enduring. Modern technologies, from lasers and semiconductors to atomic clocks and quantum computing, rely on the precise understanding of electron transitions and energy quantization. These technological advances, which have reshaped communication, medicine, and information technology, are direct descendants of Bohr's insight into atomic stability. Ultimately, Bohr's introduction of fixed energy levels for electrons provided a solution to one of the most perplexing problems in physics, reconciling theory with observation and transforming our understanding of the atom. It revealed that stability, structure, and the emission of light are governed by quantized rules, reshaping the foundations of science and inspiring generations of physicists to explore the extraordinary principles of the quantum world. Bohr showed that by embracing a new way of thinking, grounded in evidence and bold reasoning, humanity could uncover the hidden order behind the apparent chaos of nature. One of the most remarkable achievements of Niels Bohr's atomic theory was its ability to explain the emission and absorption of light in discrete spectral lines. Before Bohr, the emission spectra of elements presented a perplexing puzzle. When scientists passed light through a prism, they observed sharp, distinct lines of color rather than a continuous rainbow. Each element seemed to produce its own unique pattern, a spectral fingerprint, yet classical physics offered no explanation for this phenomenon. According to classical theories, electrons orbiting the nucleus should emit radiation continuously, producing a broad, unbroken spectrum of light. The sharp lines that appeared in experiments were mysterious and contradictory to everything physicists believed they understood about the atom. These patterns begged a new framework, a revolutionary way of thinking that could reconcile experimental observations with theoretical models. Bohr provided that framework. Bohr proposed that electrons occupy fixed energy levels around the nucleus and that they can transition between these levels by absorbing or emitting a specific amount of energy. This energy is not arbitrary, but is quantized, corresponding exactly to the difference between the two energy levels involved in the transition. When an electron jumps from a higher energy level to a lower one, it emits a photon of light with an energy precisely equal to this difference. Conversely, when an electron absorbs energy, it can move to a higher energy level. This simple yet profound concept explained why spectral lines appear as discrete colors rather than continuous spectrum. Each line represents a photon emitted or absorbed during a specific electronic transition, providing a direct glimpse into the quantized nature of the atom. The success of Bohr's model in explaining spectral lines was both dramatic and far-reaching. The hydrogen atom, the simplest element, served as the initial proving ground. Bohr demonstrated that the wavelengths of light observed in hydrogen's emission spectrum could be precisely predicted by his theory. Experimental data matched Bohr's calculations with astonishing accuracy, providing strong evidence for the validity of his ideas. This success was groundbreaking because it linked an abstract theoretical concept, quantized energy levels, with observable, measurable phenomena. For the first time, scientists had a clear and predictive model that explained why atoms emit light in specific patterns. The spectral lines were no longer mysterious artifacts. They became tangible proof of the underlying quantum structure of matter. Beyond hydrogen, Bohr's model inspired further research into the spectra of more complex atoms. While the model itself needed refinement to fully explain heavier elements, it established the fundamental principle that electrons exist in discrete energy levels and that light emission occurs through quantized transitions. This insight laid the groundwork for the development of modern quantum mechanics, where the behavior of electrons in atoms and molecules is described with even greater precision using wave functions and probability distributions. The discrete emission of light, once puzzling, became a cornerstone of atomic theory and a guiding principle for future discoveries. Bohr's explanation of spectral lines also had profound implications for our understanding of energy in the microscopic world. It demonstrated that energy is not continuous at the atomic level, but comes in distinct packets or quanta. This reinforced Max Planck's earlier revolutionary idea and showed that quantization is a fundamental property of nature. Light, electrons, and even the very structure of atoms follow rules that are inherently discrete, challenging classical assumptions about smooth, continuous behavior. By connecting energy quantization with observable phenomena, Bohr provided a bridge between theory and experiment, showing that abstract principles could be directly tested and verified. The practical impact of this understanding has been enormous. Knowledge of electronic transitions and spectral lines underpins much of modern technology. Spectroscopy, the study of the interaction between light and matter, allows scientists to identify the composition of distant stars, analyze chemical compounds, and develop lasers and other quantum-based devices. Each of these applications relies on the precise understanding that Bohr's model first provided, that electrons occupy fixed energy levels and that light is emitted or absorbed in discrete quantities. Furthermore, Bohr's explanation of spectral lines reshaped the philosophical understanding of the universe. It revealed a world governed by quantized rules, where energy changes are not continuous but occur in distinct steps. Observation, measurement, and experimental verification became central to scientific inquiry, and the idea of discrete atomic structure challenged the deterministic world view of classical physics. The universe at the microscopic level was no longer entirely predictable. It followed rules that were probabilistic, quantized, and often counterintuitive. Ultimately, Bohr's explanation of the emission and absorption of light stands as one of the most elegant achievements in the history of science. It demonstrated the power of combining theoretical insight with experimental evidence, transforming a once mysterious phenomenon into a clear and predictable process. By revealing the discrete, quantized nature of atomic transitions, Bohr not only solved a long-standing puzzle, but also opened a window into the deeper principles that govern the quantum world. The spectral lines of hydrogen and other elements became more than patterns of color. They became symbols of the hidden order of the universe and the triumph of human understanding over nature's mysteries. The contributions of Max Planck and Niels Bohr revealed a universe far stranger and more intricate than anyone had previously imagined. Their combined insights demonstrated that nature does not always follow the smooth, continuous patterns predicted by classical physics, but operates according to fundamentally quantized principles. The idea that energy is composed of discrete packets, or quanta, and that electrons occupy fixed energy levels, challenged centuries of conventional thinking and reshaped the very foundations of science. Together, their discoveries created a new lens through which to observe and understand the microscopic world, transforming both theory and experiment in ways that continue to resonate in modern physics. The realization that nature operates in discrete steps fundamentally altered the way scientists approached physical problems. Before Planck, it was assumed that energy and motion were continuous and infinitely divisible. that the universe behaved like a perfectly predictable machine. Planck's introduction of quanta shattered this assumption. By demonstrating that energy is exchanged in discrete amounts, he provided a framework that not only explained the problem of blackbody radiation, but also suggested that the behavior of matter and light is governed by rules that differ radically from everyday experience. Bohr extended this insight into the realm of the atom. His postulation that electrons occupy fixed energy levels explained why atoms are stable and why light is emitted in discrete spectral lines. These revelations revealed that the microscopic world has its own intrinsic order, governed by quantized principles that classical physics could not describe. The significance of quantization cannot be overstated. By introducing discrete energy levels and fundamental constants like Planck's constant, these pioneering scientists gave physics the tools to describe phenomena that were previously mysterious or paradoxical. The behavior of electrons, the emission of photons, and the interactions between atoms and light could now be predicted with remarkable accuracy. Classical laws, which had excelled in describing planetary motion and macroscopic systems, were shown to be incomplete when it came to the atomic and subatomic scales. Quantum rules governed these realms, introducing probabilistic behavior, wave, particle duality, and intrinsic uncertainties. The world of the very small was no longer a mirror of the macroscopic universe. It followed its own distinct laws, elegant yet counterintuitive, precise yet probabilistic. Planck and Bohr's combined contributions also had profound philosophical implications. Their discoveries suggested that reality itself is not wholly deterministic. Where Newtonian mechanics had allowed the prediction of future events with perfect certainty if initial conditions were known, quantum principles introduced inherent unpredictability. The idea that an electron could only exist in certain energy levels, and that energy could only be exchanged in discrete amounts, forced scientists to recognize that some aspects of the universe are governed by fundamental probabilities rather than certainties. This shift challenged long-held assumptions about the nature of reality, inviting scientists, philosophers, and thinkers to reconsider what it means to understand the world around us. Beyond theory, the practical consequences of their work have been enormous. The recognition of quantized energy in electron orbits underpins virtually all modern technology. Semiconductors, lasers, nuclear energy, quantum computers, and even the devices we use daily, smartphones, computers, medical imaging equipment, rely on principles first illuminated by Planck and Bohr. By understanding that electrons move between discrete energy levels and that energy itself is quantized, scientists and engineers gained the ability to manipulate matter and light at the atomic and subatomic levels. Their insights bridged the gap between fundamental theory and practical application, transforming both our understanding of the universe and our capacity to harness its properties for human advancement. Their work also inspired generations of scientists to push the boundaries of knowledge even further. Quantum mechanics, built upon the foundation laid by Planck and Bohr, has become one of the most successful and precise scientific frameworks in history. It describes the behavior of particles and forces with astounding accuracy, explains phenomena that classical physics could not, and continues to provide the basis for cutting-edge research in fields ranging from cosmology to condensed matter physics. Every advancement in the quantum domain, from the development of the transistor to the creation of quantum encryption, owes a debt to the daring and originality of these two visionaries. Ultimately, Planck and Bohr revealed a universe governed by rules that are subtle, quantized, and profoundly different from everyday experience. Their discoveries demonstrated that the microscopic world operates under principles that are distinct from the macroscopic reality we observe, and that understanding these principles requires bold imagination combined with rigorous scientific reasoning. By challenging assumptions, embracing the unfamiliar, and linking abstract theory to observable phenomena, they forever changed our perception of the universe. Their work serves as a powerful reminder that nature often hides its most profound truths in ways that defy intuition, and that human curiosity, guided by insight and evidence, can illuminate even the deepest mysteries. The revolutionary insights of Max Planck and Niels Bohr did more than challenge the existing understanding of physics. They laid the foundation for technological advancements that would reshape the modern world. By demonstrating that energy is quantized and that electrons occupy fixed energy levels, they provided the principles necessary for a range of innovations that touch nearly every aspect of daily life. Quantum physics, born from their ideas, opened a pathway to manipulate matter and energy at the atomic and subatomic levels, enabling humanity to harness phenomena that classical physics could never explain or control. The recognition that the microscopic world operates under discrete rules was not merely theoretical. It became the bedrock for technologies that have transformed society. One of the most immediate and practical applications of their work is in the field of semiconductors. Semiconductors are materials whose electrical properties can be precisely controlled, and their behavior depends directly on the quantized energy levels of electrons. Understanding electron transitions, as Bohr's model predicted, allows engineers to design materials that conduct electricity in specific ways. This knowledge is the foundation for modern electronics, including computers, smartphones, and countless other devices. The ability to control the movement of electrons in semiconductors underpins the digital revolution, demonstrating how abstract principles of quantum theory can produce tangible, transformative effects in everyday life. The invention of lasers is another powerful testament to the practical significance of quantized energy levels. Lasers rely on the principle that electrons can be excited to higher energy states and then release photons of precise energy when they return to lower levels. This process, known as stimulated emission, was predicted by quantum theory and directly depends on the discrete nature of energy. Lasers have become indispensable tools in medicine, communication, industry, and scientific research. From delicate eye surgeries to high-speed fiber optic communications, lasers exemplify how the quantized behavior of atoms can be harnessed to achieve remarkable precision and efficiency in the real world. Beyond these technological applications, Planck and Bohr's discoveries have also profoundly influenced spectroscopy, the science of analyzing light to determine the composition of matter. By understanding that electrons transition between quantized energy levels, scientists can interpret the light emitted or absorbed by elements to identify their presence and properties. This technique is central to astronomy, where it allows researchers to determine the chemical composition of distant stars and galaxies. It is also critical in chemistry, materials science, and environmental monitoring, providing a window into both the cosmos and the microscopic structure of matter on Earth. The ability to read the signatures of elements through light is a direct consequence of the principles first revealed by Planck and Bohr. Moreover, the implications of their work extend into cutting-edge fields like quantum computing and quantum cryptography. Quantum computers exploit the principles of superposition and entanglement, which are rooted in the discrete, probabilistic nature of quantum states. Qubits, the fundamental units of quantum information, rely on the controlled manipulation of electrons and photons at the quantum level. Without an understanding of energy quantization and electron behavior, these technologies would be impossible. Similarly, quantum cryptography leverages the principles of quantum mechanics to create communication systems that are fundamentally secure, relying on the intrinsic uncertainties and quantized states of particles, These innovations demonstrate that the abstract insights of Planck and Bohr are not merely academic. They are essential to the forefront of technological progress. The influence of quantization also reaches into fundamental science. Particle physics, nuclear energy, and even cosmology depend on the understanding that energy and matter behave in discrete, predictable ways at the smallest scales. By introducing quantized energy levels and a fundamental constant, Planck and Bohr provided a framework for investigating the subatomic world, explaining phenomena that classical physics could not, and inspiring generations of scientists to explore realms previously thought inaccessible. Their work enabled a scientific revolution, transforming our ability to measure, predict, and control nature with unprecedented accuracy. Ultimately, the recognition of quantized energy and electron transitions illustrates the profound impact that theoretical insights can have on practical human achievement. What began as a solution to a theoretical problem, the explanation of Blackbody radiation and atomic stability, evolved into the foundation for technologies that define the modern era. The discrete nature of energy and electrons, revealed by Planck and Bohr, has allowed humanity to harness light, electricity, and information in ways that would have been unimaginable a century ago. Their work exemplifies the extraordinary power of scientific discovery, showing that understanding the fundamental rules of the universe can lead to innovations that transform both knowledge and everyday life. One of the most inspiring lessons from the work of Max Planck and Niels Bohr is that scientific progress often emerges not from confirming what is already known, but from questioning assumptions that have long been accepted as truths. At the turn of the 20th century, classical physics had achieved remarkable success in explaining the macroscopic world. Newton's laws described the motion of planets and projectiles with astonishing precision, and Maxwell's equations unified electricity and magnetism into a coherent framework. Yet, despite these triumphs, cracks were appearing in the classical model, particularly at the atomic and subatomic scales. Phenomena such as Blackbody radiation, the photoelectric effect, and the discrete spectral lines of hydrogen challenged conventional thinking. Many physicists assumed that classical mechanics and electrodynamics were sufficient to explain all natural phenomena. Planck and Bohr demonstrated that progress required boldness, the courage to question the foundations of established knowledge and to propose entirely new frameworks. Max Planck exemplified this approach when he introduced the concept of energy quanta. The prevailing belief was that energy could vary continuously, flowing smoothly in all processes. Classical physics could not explain the pattern of Blackbody radiation. It predicted infinite energy emission at high frequencies, a result known as the ultraviolet catastrophe. Planck's radical insight was that energy is emitted and absorbed in discrete packets, or quanta, whose size is proportional to the frequency of the radiation. This simple yet revolutionary idea resolved the problem and provided the first glimpse of a universe governed by quantum rules. His willingness to challenge the continuous view of energy demonstrated that progress in science often requires questioning long-held assumptions, even those that appear universally accepted. Niels Bohr carried this spirit of bold questioning into the realm of atomic structure. Classical mechanics predicted that electrons orbiting a nucleus would radiate energy continuously, eventually spiraling into the nucleus and causing the atom to collapse. Yet matter is remarkably stable, and spectral lines observed in laboratory experiments revealed discrete energy patterns that classical physics could not explain. Bohr proposed that electrons occupy fixed energy levels, jumping between orbits only by absorbing or emitting precise amounts of energy. This audacious hypothesis solved multiple problems simultaneously. It explained atomic stability, accounted for the discrete spectral lines of hydrogen, and demonstrated that energy at the microscopic level is inherently quantized. Bohr's willingness to challenge the classical assumptions about continuous electron motion exemplified the kind of intellectual courage necessary to expand the boundaries of scientific knowledge. The broader significance of Planck and Bohr's work lies in the lesson it offers about the nature of discovery. Scientific advancement is rarely linear. Classical physics had succeeded in explaining many phenomena, but its limitations became evident when confronted with the microscopic world. Rather than forcing experimental results to fit pre-existing theories, Planck and Bohr allowed the evidence to guide their thinking, even when it led to revolutionary conclusions. This approach underscores a critical principle of science. Progress often comes from embracing the unexpected and being willing to rethink fundamental concepts. Their discoveries were not incremental improvements. They represented conceptual leaps that forever changed our understanding of the universe. Their work also illustrates the interplay between theory and experiment. Planck's formulation of energy quanta was mathematically elegant, but it was firmly grounded in the experimental data of Blackbody radiation. Bohr's model, likewise, connected theoretical postulates about quantized electron orbits with observable spectral lines. By aligning theory with empirical evidence, they demonstrated that revolutionary ideas in science must not only be imaginative but also verifiable. This balance between creativity and rigor is a hallmark of transformative scientific thinking. Beyond physics, the courage of Planck and Bohr has philosophical and cultural implications. Their readiness to challenge established norms reminds us that intellectual progress requires both curiosity and boldness. It is a lesson that extends beyond the laboratory, emphasizing the importance of questioning assumptions, exploring unconventional ideas, and remaining open to new perspectives. The revolutionary nature of quantum physics serves as a testament to the power of human ingenuity when guided by both observation and imagination. Ultimately, the work of Planck and Bohr teaches us that the path to discovery is often paved by those willing to see the world differently. By questioning classical assumptions, introducing new principles, and grounding their ideas in experimental evidence, they reshaped the foundations of physics and inspired generations of scientists to explore the unknown. Their legacy reminds us that curiosity, courage, and creativity are essential ingredients for advancing knowledge, and that the willingness to challenge convention can illuminate truths about the universe that would otherwise remain hidden. The influence of Max Planck and Niels Bohr on subsequent generations of physicists cannot be overstated. Their pioneering ideas about quantization and atomic structure laid the groundwork for a new era of scientific exploration, inspiring countless researchers to delve deeper into the mysteries of the quantum world. Long after Planck introduced the concept of energy quanta and Bohr formulated his model of the atom, their work continued to shape the thinking of some of the greatest minds in physics, including Albert Einstein, Werner Heisenberg, Erwin Schrödinger, and Paul Dirac. These scientists took the foundation built by Planck and Bohr and expanded it into a comprehensive framework known today as quantum mechanics, which has revolutionized our understanding of matter, energy, and the universe itself. Planck's and Bohr's contributions provided a conceptual map for scientists exploring atomic and subatomic phenomena. Planck showed that energy is not a continuous flow, but exists in discrete packets, which provided the first clue that the microscopic world follows rules fundamentally different from classical physics. Bohr demonstrated that electrons occupy fixed energy levels within the atom, and that light is emitted or absorbed when electrons transition between these levels. Together, these insights revealed a hidden order in the behavior of matter and energy, one that could be described mathematically and verified through experimentation. For subsequent physicists, this framework offered both inspiration and guidance. It suggested that even the most puzzling phenomena, such as the dual particle, wave nature of light, or the probabilistic behavior of subatomic particles, could be understood if one approached the universe with imagination, rigor, and openness to new principles. Einstein, for example, built upon Planck's concept of energy quanta when he explained the photoelectric effect, showing that light itself behaves as discrete particles called photons. This insight not only confirmed the quantized nature of energy, but also extended the principles of quantum theory to electromagnetic radiation, opening the door to the development of quantum electrodynamics decades later. Einstein's work demonstrated the power of building upon foundational ideas, illustrating how Planck's initial insight could serve as a springboard for new discoveries. Bohr's model of the atom similarly influenced the work of other physicists, providing a conceptual framework for understanding the complex interactions of electrons in more complicated atoms. Werner Heisenberg and Erwin Schrödinger, two of the architects of modern quantum mechanics, directly expanded on Bohr's ideas. Heisenberg's matrix mechanics and Schrödinger's wave mechanics offered mathematical formulations that described the behavior of electrons and atoms with far greater accuracy, but both were guided by the principles Bohr had introduced: quantization of energy and the existence of discrete electron states. Bohr's idea that electrons occupy specific energy levels, and his recognition of the limits of classical descriptions, allowed these scientists to develop a theory that accounted for phenomena such as electron probability distributions, atomic spectra, and chemical bonding in complex molecules. Without the foundation laid by Planck and Bohr, the mathematical and conceptual breakthroughs of the 1920s and 1930s might never have been possible. The influence of Planck and Bohr extended beyond the technical aspects of quantum mechanics. Their work shaped the culture of physics itself, inspiring a generation of scientists to approach nature with both boldness and humility. They demonstrated that questioning deeply held assumptions, while risky, can yield profound insights. They also showed that theoretical innovation must be paired with careful observation and experimentation. This approach became a guiding principle for quantum physicists, who sought to explore realms of reality that were invisible, counterintuitive, and fundamentally different from everyday experience. The intellectual courage exemplified by Planck and Bohr set a standard for scientific inquiry, encouraging their successors to tackle questions that once seemed beyond human understanding. Planck and Bohr also left a legacy in education and communication. Bohr's model of the atom, though eventually refined, remains a fundamental teaching tool in physics and chemistry classrooms around the world. It introduces students to the principles of quantization, atomic structure, and the behavior of electrons in a way that is accessible yet profound. Planck's constant and the concept of energy quanta likewise serve as foundational concepts in understanding the quantum world, guiding both research and pedagogy. Ultimately, the impact of Planck and Bohr on future generations is a testament to the enduring power of visionary ideas. Their work did not merely solve specific scientific puzzles. It transformed the way humanity approaches the study of the universe. By laying the groundwork for quantum mechanics, they inspired generations of physicists to explore the unknown, to reconcile theory with observation, and to embrace the strange and fascinating behavior of the microscopic world. Their influence continues to shape science, technology, and our understanding of reality, proving that the bold insights of a few individuals can resonate across decades and even centuries, guiding humanity toward ever deeper comprehension of the universe. The profound influence of Max Planck and Niels Bohr extends beyond the formulation of quantum theory. It lies in the way their work reshaped the very philosophy of science. By introducing concepts that defied classical intuition, energy quanta, and fixed electron orbits, they forced scientists to rethink the nature of reality itself. Before their discoveries, the prevailing belief was that the universe was entirely deterministic, that every motion and interaction could, in principle, be predicted with absolute certainty if one knew the initial conditions. Classical mechanics, which had successfully described everything from falling apples to planetary motion, suggested a clockwork universe governed by unchanging laws. Yet Planck and Bohr demonstrated that at the microscopic level, nature behaves differently, operating under quantized rules that limit predictability and introduce inherent uncertainty. This insight represented a profound philosophical shift, challenging centuries of established thought and opening new avenues of scientific and intellectual exploration. Max Planck's introduction of energy quanta revealed that energy is not continuous, but comes in discrete packets proportional to frequency. This concept overturned the classical assumption that energy could vary smoothly in any amount. The implications were enormous. If energy changes in fixed amounts, then processes at the atomic and subatomic scales are fundamentally discontinuous. This insight resolved the problem of Blackbody radiation, which classical physics could not explain, and provided a foundation for the emerging field of quantum mechanics. Planck's constant, the proportionality factor linking energy to frequency, became one of the most important numbers in physics, establishing a bridge between the macroscopic and microscopic realms. It was a constant that defined the scale at which quantum effects dominate and provided scientists with a tool to measure and predict phenomena that had previously been inscrutable. Niels Bohr extended Planck's insight into the structure of the atom, proposing that electrons occupy specific energy levels and that light is emitted or absorbed only when electrons transition between these levels. Bohr's model explained the discrete spectral lines observed in hydrogen and other elements, resolving a puzzle that had baffled physicists for decades. By demonstrating that electrons cannot exist at arbitrary distances from the nucleus and that energy changes are quantized, Bohr provided a framework for understanding atomic stability and the interaction of matter and light. This principle of fixed energy levels revealed a hidden order in the microscopic world, where seemingly chaotic behaviors conform to precise, quantized rules. Bohr's work showed that the universe at the atomic scale is structured, intelligible, and governed by fundamental constants. Yet it is also far stranger and less intuitive than the macroscopic world we perceive. The philosophical implications of Planck's and Bohr's work are profound. They suggested that the universe is not fully deterministic. Rather, it operates according to probabilities and quantized interactions at the smallest scales. The classical notion that all events could be predicted with absolute certainty no longer applied to the quantum realm. Instead, outcomes are determined by probabilistic rules, where observation and measurement play crucial roles in defining what can be known. Bohr's later contributions, including his principle of complementarity, further emphasized that the behavior of quantum systems depends on the experimental context, highlighting the inseparability of the observer and the observed. This concept not only reshaped physics, but also inspired philosophical discussions about the limits of knowledge and the nature of reality itself. Their work also had profound practical and technological implications. By revealing the discrete nature of energy and electron behavior, Planck and Bohr laid the foundation for innovations that define the modern era. Semiconductors, lasers, quantum computing, nuclear energy, and advanced imaging technologies all rely on the principles they discovered. Understanding electron transitions and energy quantization has enabled humanity to manipulate light, electricity, and information with unprecedented precision, transforming industries, medicine, communication, and research. What began as abstract theoretical concepts evolved into practical tools that reshape daily life, demonstrating the power of fundamental scientific insight to influence technology and society. Moreover, Planck and Bohr inspired generations of scientists to explore the unknown with curiosity, creativity, and rigor. Their work encouraged physicists to challenge assumptions, embrace unconventional ideas, and seek explanations for phenomena that defy intuition. By showing that profound truths about the universe could be uncovered through a combination of imaginative thinking and meticulous experimentation, they set a standard for scientific inquiry that continues to guide research today. Their legacy is a testament to the transformative power of questioning, exploration, and intellectual courage. Ultimately, the work of Planck and Bohr represents a turning point in human understanding of the universe. By introducing energy quanta and fixed electron orbits, they revealed a universe that is at once structured, probabilistic, and profoundly counterintuitive. Their discoveries transformed not only physics, but also our philosophical perspective on nature, knowledge, and the limits of human understanding. Through their insights, they illuminated the hidden order of the microscopic world, forever changing the way we see reality and demonstrating the extraordinary power of human curiosity guided by observation, reasoning, and imagination. The exploration of the quantum world by Max Planck and Niels Bohr marked a profound transformation in humanity's understanding of nature, but it also laid the groundwork for a new perspective on scientific inquiry itself. Their work demonstrated that progress in physics requires both rigorous observation and bold theoretical innovation. Classical physics had achieved extraordinary success in describing macroscopic phenomena, yet its principles faltered when confronted with the microscopic world of atoms and subatomic particles. Planck's quantization of energy and Bohr's model of fixed electron orbits revealed that nature at its smallest scales operates under rules radically different from those governing everyday experience. This recognition not only changed physics, but also redefined the approach scientists must take when exploring the unknown. It illustrated that theory alone is insufficient without empirical grounding, and that experimentation without conceptual insight can leave the most profound phenomena unexplained. Max Planck's introduction of the quantum of energy was a paradigm shift in the truest sense. At the time, physicists were struggling to explain Blackbody radiation, which seemed to contradict classical theory. The ultraviolet catastrophe, an absurd prediction that objects would emit infinite energy at short wavelengths, highlighted the limitations of existing laws. Planck proposed that energy is emitted or absorbed in discrete units, now called quanta, each proportional to the frequency of the radiation. This simple, elegant hypothesis resolved the experimental discrepancies and revealed that energy at the microscopic level is inherently quantized. It marked the beginning of a new era, where the universe was understood not as a smooth continuum, but as a lattice of discrete events and interactions. Planck's insight illustrated the power of thinking beyond accepted frameworks, showing that one profound idea can rewrite the rules of science. Niels Bohr extended this revolutionary thinking to the structure of the atom, addressing a problem that had long vexed physicists: why atoms are stable and why they emit light in discrete spectral lines. Classical mechanics predicted that electrons orbiting a nucleus should radiate energy continuously, eventually spiraling into the nucleus. Observations, however, revealed discrete spectral lines and remarkably stable matter, suggesting that classical assumptions were incomplete. Bohr postulated that electrons occupy fixed energy levels, or shells, and that they can jump between these levels only by absorbing or emitting precise amounts of energy. These transitions account for the discrete spectral lines observed in hydrogen and other elements. Bohr's model provided an elegant explanation for atomic stability, the emission of light, and the quantized behavior of matter. It demonstrated that the microscopic world is governed by order and precision, but in ways that defy classical intuition. The combination of Planck's and Bohr's discoveries provided a framework that would inspire generations of physicists to push the boundaries of understanding. Their work revealed that quantum phenomena are governed by precise, discrete rules, which could be predicted, calculated, and experimentally verified. This realization guided future research into atomic structure, chemical bonding, and particle behavior, leading to the development of quantum mechanics by scientists such as Heisenberg, Schrödinger, and Dirac. Their advances showed that the principles laid out by Planck and Bohr were not limited to specific problems, but represented universal features of the microscopic world. The implications extended far beyond physics, influencing chemistry, materials science, and even emerging technologies that rely on precise control of electrons and photons. The philosophical implications of their work are equally profound. By demonstrating that energy and matter are quantized, Planck and Bohr revealed a universe that is fundamentally probabilistic at the smallest scales. The deterministic world view of classical mechanics gave way to a perspective in which outcomes are governed by probabilities, and observation itself plays a role in defining reality. Bohr's principle of complementarity, which emphasized that different experimental setups reveal different aspects of quantum systems, further reinforced the idea that reality is not always fixed, but depends on context. These insights reshaped not only physics, but also our understanding of the limits of knowledge, highlighting that even the most precise measurements are subject to inherent uncertainty. Practically, their work enabled technological advancements that define modern life. Semiconductors, lasers, nuclear energy, quantum computing, and spectroscopy all rely on principles derived from Planck's and Bohr's theories. By understanding discrete energy levels and the quantized nature of atomic interactions, scientists can manipulate light, electricity, and information with extraordinary precision. This interplay between fundamental discovery and practical application illustrates the enduring value of their work. Abstract ideas can produce transformative innovations that touch every aspect of human existence. Ultimately, Planck and Bohr demonstrated that progress in science requires both imagination and rigor. By questioning classical assumptions, proposing bold theoretical frameworks, and grounding their insights in empirical evidence, they illuminated the hidden structures of nature. Their legacy continues to inspire physicists to explore the unknown, to reconcile theory with observation, and to embrace the strange yet ordered behavior of the quantum world. They taught us that the pursuit of knowledge demands curiosity, courage, and a willingness to challenge convention, and that the rewards of such endeavors can forever change our understanding of the universe. The legacy of Max Planck and Niels Bohr is a story of curiosity, daring, and the relentless pursuit of understanding. Their discoveries did more than illuminate the workings of the atom. They fundamentally reshaped humanity's comprehension of the universe and our place within it. At the heart of their work lies a profound lesson: that the natural world often operates according to rules far more subtle and intricate than everyday experience suggests. By uncovering the principles of energy quantization and fixed electron orbits, Planck and Bohr revealed a universe governed by precise, yet counterintuitive, laws. Their insights demonstrated that the microscopic world is structured, measurable, and comprehensible, but only if one is willing to look beyond classical assumptions and embrace the unfamiliar. Max Planck's introduction of quanta was the spark that ignited the quantum revolution. He recognized that classical physics could not account for Blackbody radiation, a problem that had confounded scientists for decades. The prediction of infinite energy emission at high frequencies, known as the ultraviolet catastrophe, starkly contradicted experimental evidence. Planck proposed that energy is not a continuous flow, but comes in discrete packets, or quanta, with each quantum proportional to the frequency of radiation. This concept, simple in its formulation, yet revolutionary in implication, provided a solution to the experimental anomaly and laid the groundwork for a new understanding of energy and matter. Planck's courage to challenge centuries of established thought exemplified the audacity required to advance scientific knowledge. Building upon Planck's insight, Niels Bohr tackled the perplexing problem of atomic structure. Classical mechanics suggested that electrons orbiting the nucleus should continuously lose energy, eventually collapsing into the nucleus, a prediction that conflicted with the observed stability of matter. Bohr proposed that electrons occupy fixed energy levels or shells and can only move between these levels by absorbing or emitting discrete amounts of energy. This model not only explained the discrete spectral lines of hydrogen, but also introduced the principle of atomic stability, demonstrating that atoms are ordered, predictable systems rather than chaotic collections of particles. Bohr's insights showed that the quantum rules governing the microscopic world are both elegant and consistent, providing a framework that could guide experimentation and theoretical development for decades to come. The work of Planck and Bohr exemplifies the intricate relationship between theory and experiment. Planck's hypothesis arose from careful observation of Blackbody radiation, while Bohr's model was informed by the spectral patterns of hydrogen. Their discoveries illustrate that transformative science depends on the interplay between empirical evidence and conceptual innovation. Neither could have achieved their breakthroughs in isolation. Each relied on existing knowledge, experimental data, and a willingness to challenge assumptions. Together, their contributions created a cohesive framework that allowed subsequent physicists to explore the quantum world with precision, leading to the development of modern quantum mechanics by Heisenberg, Schrödinger, Dirac, and others. Beyond their scientific achievements, Planck and Bohr's discoveries reshaped the philosophical landscape of physics. By revealing that energy and matter are quantized and that electrons occupy fixed orbits, they challenged the deterministic worldview of classical mechanics. The microscopic universe behaves probabilistically, governed by discrete transitions and rules that cannot always be intuitively understood. Bohr's principle of complementarity emphasized that observation plays a crucial role in defining quantum systems, illustrating that reality is not entirely independent of the observer. These insights transformed our understanding of knowledge, measurement, and the nature of reality itself, demonstrating that the universe is more subtle and complex than it appears at first glance. The practical implications of their work are equally profound. Technologies that shape modern life, lasers, semiconductors, quantum computing, spectroscopy, and nuclear energy, rely on the principles first articulated by Planck and Bohr. By understanding discrete energy levels and the quantized behavior of matter, scientists and engineers can manipulate atoms, electrons, and photons with remarkable precision. The abstract concepts of quantum theory thus evolved into tools that have revolutionized communication, medicine, information technology, and scientific research. This connection between fundamental discovery and practical application illustrates the enduring power of their insights. Ultimately, the legacy of Planck and Bohr lies not only in the scientific truths they uncovered, but also in the spirit of inquiry they embodied. Their work reminds us that curiosity, imagination, and a willingness to challenge convention are essential for progress. By questioning classical assumptions, proposing revolutionary models, and rigorously testing their ideas against observation, they transformed physics and opened the door to a deeper, more nuanced understanding of the universe. Their discoveries demonstrate that the pursuit of knowledge is both a practical and philosophical endeavor, one that can illuminate the hidden structures of nature and inspire generations to explore the unknown. Through their courage, insight, and relentless pursuit of truth, Max Planck and Niels Bohr changed the course of science. They revealed that the microscopic world operates under precise quantized laws, challenging classical intuition and expanding the boundaries of human understanding. Their legacy endures, not only in the technologies and theories that shape modern life, but also in the example they set for all who seek to uncover the hidden truths of the universe. The quantum revolution they initiated continues to inspire, proving that the universe, in all its complexity, rewards those who dare to look deeper, think differently, and question what has long been taken for granted.